Hi guys, my name is Samuel Jasper. I'm from CIC department, currently in my first year. My topic for AIT concept video in for applied physics is properties of matter. Introduction. Matter waves, also known as de Broglie waves, are a fundamental concept in quantum mechanics that describe the wave-like nature of particles. This idea was first proposed by French physicist Louis de Broglie in 1924 and revolutionized our understanding of the behavior of matter at the quantum scale. Key points about matter waves. Wave particle duality. De Broglie's hypothesis states that every particle, such as an electron or a proton, has both particle-like and wave-like properties. This is an extension of the idea of a wave-particle duality, which was earlier observed in light. De Broglie wavelength. The wavelength lambda associated with a particle is given by lambda is equal to h by lambda, where h is Planck constant and its value is 6.626 into 10 power minus 34 joules, and where p is the momentum of the particle, p is equal to mv for non-realistic particles. Wave particle duality. Wave-particle duality is a fundamental concept in quantum mechanics, stating that every particle or quantum entity can exhibit both wave-like and particle-like properties depending on the type of the experiment performed. This duality applies to both light and matter, performing the cornerstone of quantum theory. Wave-like behavior. Particles like photons, electrons, and even atoms can exhibit wave-like particles such as interference and diffraction. In interface, waves overlap where they can interface constructively or destructively. In diffraction, waves can bend around obstacles or spread out after passing through narrow openings. Wave-particle duality in light. As a wave described by Maxwell's equations, light behaves as an electromagnetic wave exhibiting interface and diffraction. For example, light passing through a prism, it bends and disperses into a spectrum. As a particle, light consists of a discrete packets of energy called photons. The formula for energy of a photon is equal to E is equal to h, where h is a Planck constant and E is the frequency. Implications of wave-particle duality. Complementary principle. It was proposed by Niels Bohr. It states that wave and particle behaviors are complementary aspects of quantum systems. You can observe either property, but not both simultaneously. Quantum mechanics framework. The duality is captured by the wave-particle psi, which provides the probability distribution for particles' position and momentum. Applications. Quantum technologies. A wave-particle duality underlies quantum community, quantum cryptography, and quantum sensors. Electron microscopy. The wave-like behavior of electron is used to achieve high-resolution imaging. Semiconductor. Understanding electron behavior in solid relies on both wave and particle perspective. We'll see more depth into it later on. Double-slit experiment. Setup. A coherent source of particles like photons, electrons, or even atoms is aimed at a barrier with two slits. A screen is placed behind the slits to detect the particles. Observations. Without observation, when particles are not measured at the slit, an interface pattern appears on the screen resembling the pattern observed and found by waves. This indicates that a particle passed through both a slits simultaneously behaving like waves and interfering with themselves. With observation, where detectors are placed to measure which slit a particle passes through, the interface pattern disappears. The particle behaves like classical particles forming two distinct clusters on screen corresponding to the two slits. Its significance. It demonstrates the quantum entities exhibit wave-like behavior when not observed and particle-like behavior when observed. The act of measurement collapses the wave function, forcing the particle to take a definite path. Electron diffraction. It is also known as Davison-Germer's experiment. Its setup. In 1927, Clinton Davison and Lester Germer directed a beam of electrons at a crystalline nickel target. Electrons scattered off the atoms in a crystal lattice and their angular distribution was measured. Observations. The electrons produced a diffraction pattern on the detector consisting of bright and dark regions. This pattern is a characteristic of waves interacting with a periodic structure. In this case, it is the crystal lattice. Explanation. According to de Broglie hypothesis, electrons have a wavelength h is equal to, lambda is equal to h by lambda, where p is equal to mv is the momentum of the electron. The observed diffraction pattern matched the theoretical predictions based on the de Broglie wavelength. Its significance. It confirms that electrons, despite being particles, exhibit wave-like properties under certain conditions. Showed that matter waves are real and measurable. De Broglie hypothesis. Key points of the de Broglie hypothesis. Wave-particle duality for matter. Just as light exhibits both wave-like and particle-like properties, de Broglie proposed that matter behaves similarly. A moving electron, for example, behaves like a wave with a wavelength lambda determined by its momentum. Applications. De Broglie hypothesis was particularly significant for electrons as it provided an explanation for electron diffraction patterns observed in experiments like Davison-Germer's experiment. Since the wavelength of an electron is much smaller than visible light, its wave-like properties are observable under certain conditions. De Broglie wavelength in practice. For macroscopic objects, the momentum is large, making the wavelength extremely small and undetectable. For microscopic particles like electrons and protons, the de Broglie wavelength is significant, and their wave-like properties can be observed experimentally. Mathematical formula: the wavelength associated with a particle is given by h lambda is equal to h by p, where p is equal to m mass into velocity, and it is also known as momentum. Experimental confirmation. The Davison-Germer experiment provided direct experimental evidence for de Broglie hypothesis. When electrons were scattered off a crystal, they produced a diffraction pattern similar to the behavior of waves, confirming that electrons have wave-like properties. The significance. De Broglie's hypothesis was a major breakthrough in quantum mechanics as it intended the concept of wave-particle duality previously applied to light to all particles. This laid the groundwork for the development of quantum mechanics and quantum field theory, where the wave function is used to describe the probabilities of particle positions and momentum. Properties of matter waves. Interference and diffraction. Matter waves can interfere and diffract just like light waves interfere. When two matter waves overlap, they can interfere constructively or disconstructively. Diffraction. When matter waves pass through narrow openings or round obstacles, they spread out, forming patterns similar to those of light waves. Amplification. This like behavior of matter explains phenomena such as electron diffraction in crystal lattice, which is also known as Davison and German experiment. It is also why matter waves can be used in technologies like electron microscopy, which exploits diffraction to image at the atomic level. The superposition principle. Matter waves obey the principle of superposition, meaning that when two or more matter waves overlap, the resultant wave function is the sum of the individual wave function. This is to constructive interference or disconstructive interference. Implication. The superposition principle is responsible for quantum interface effects where particles can exist in multiple states at once. This principle is a key in experiments such as double slit experiment, where interface pattern emerges from a single particle passing through both slits simultaneously. Quantization. Matter waves led to quantization of certain properties such as energy and angular momentum in systems confined to discrete regions. For example, in a particle in a box scenario, the energy levels of the particle are quantized, meaning they can only take certain discrete values based on the wavelength of the matter. Applications: electron microscopy. The wave-like properties of particularly their small de Broglie wavelength, allow them to be used for high resolution image. How it works? Electron microscopes use electron waves to illuminate a sample. Due to their small wavelength, electrons can resolve details at the atomic level, providing much higher resolution than optical microscope. Its application: transmission electron microscopes used for imaging thin slices of material to study cellular structures, material sciences, and nanotechnology. Scanning electron microscopes used for 3D surface imaging of objects at a very high level magnification. Quantum tunneling. Matter waves waves can tunnel through barriers even if the particle doesn't have enough classical energy to overcome them. In quantum mechanics, the probability of a particle being found in classically forbidden region is non-zero. This is known as quantum tunneling. Applications. Quantum tunneling is a crucial in the operation of modern semiconductor devices like transistors. It allows for miniaturization of components in integrated circuits, which is essential for advancing technologies. STM uses quantum tunneling to image surface at the atomic level. It provides insights into surface properties and it's widely used in nanotechnology and material sciences. Quantum computing. Quantum computing relies on quantum state superposition and entanglement, which are closely related to the wave-like nature of particles. Matter. Matter waves through their wave functions can exist in multiple states simultaneously, allowing quantum computers to perform complex calculations much faster than classical computers for certain tasks. Application. Quantum algorithms. Algorithms like Shor algorithms can exploit quantum superposition and interface effects. Quantum computers can stimulate physical streams that are computationally difficult or impossible for classical computers. Nuclear magnetic resonance. The wavelength behavior of matter, particularly in relation to the interaction of nuclear spins with magnetic fields, is the basis of NMR and MRI. NMR measures the resonance frequencies of atomic nuclei when exposed to a magnetic field. The wave-like nature of particles give insight into their energy states and allows the construction of detailed images of the internal structures of objects. Limitations. While the concept of matter waves has revolutionized our understanding of quantum mechanics and has many practical applications, there are several limitations and challenges associated with the behavior of matter waves, especially when it comes to their detection, interpretation, and uses in technology. This limitation arises due to the inherent principles of quantum mechanics and practical concepts in experimental settings. Invisibility for macroscopic objects. For macroscopic objects, the de Broglie wavelength becomes extremely small and practically undetectable. As the mass of an object increases, its wavelength decreases, becoming so tiny that its wave-like properties cannot be observed. This makes it impossible to detect or measure the wave-like behavior of a large object directly. Wave-particle duality. Wave-particle duality is most noticeable in microscopic systems, but it becomes less relevant for larger systems. In quantum mechanics, the wave function represents the probability of finding a particle in a particular state. For microscopic systems with many particles, the wave function becomes increasingly complex for classical dispersions dominate. Difficulty in detecting matter wave. For detecting the wave-like behavior of matter is much harder than observing particle behavior. For instance, in the electron diffraction experiments, we rely on the ability to observe interference patterns created by electron waves. However, setting up experiments that can clearly demonstrate wave behavior often requires very precise conditions and specialized equipment. Conclusion. Matter waves are a fundamental concept in quantum mechanics that reveal the wave-like nature of particles, challenging our classical understanding of matter and energy, which was proposed by Louis de Broglie in early 20th century. Matter waves introduced the idea that all particles, including electrons and atoms, exhibit both wave-like and particle-like behavior, a phenomenon also known as wave-particle duality. Electron microscopy for high resolution imaging at the atomic level. quantum computing, which leverages quantum states like superposition and entanglement for computational power far beyond classical systems. Electron diffraction and atomic interference for probing material structure and measuring quantum effects with a high precision applications in medical technologies such as MRI and MNR, which rely on quantum behavior for imaging biological applications. Thank you.